Hello, students, and welcome back from the break. I hope that you have enjoyed your time off. Now, obviously, during that time off, there's probably been some forgetting that's occurred, so I thought that we would kind of review a little bit on what the sampling distribution is. Now, first, I'm going to give you two properties of the sampling distribution. The first property of the sampling distribution is that it is weird. Okay? You're going to find it weird. You're going to find it strange and abstract. That's fine. We're still going to look at it because of the second property of sampling distributions, which is that they are necessary. They are necessary to draw any kind of conclusions in experimental research. So, for example, I talked about last semester the idea of statistical significance. So, like, for example, let's say that I'm interested in seeing if this drug I've come up with, I think it might help people, I think it might help long distance runners in their training. I think it'll cause them to have faster times during their races. But how do I know? Well, I have to do an experiment. I'd have to say grab 20 runners, randomly assign 10 of them to get to be in the control group. All right, so they might receive a placebo, so they don't receive the actual drug, they receive sugar pills, things that aren't going to actually affect their performance. All right. Whereas I give the actual new performance enhancer to the other 10 of those 20 runners. All right. And so I give 10 of them the performance enhancer, the other 10 receive a placebo. All right. And then I'll have them all run a mile a month later and see if those who are taking the performance enhancing drug run better overall. If they don't, then we know that my drug doesn't actually have that benefit that I thought it would. All right, but let's say that the people that took the drug, the performance enhancing substance, let's say that their mile time on average was 1 second faster than the control group. Just 1 second. So technically, their average time, their average performance was better, but it was so little, the difference is so little, we would say that that may not be statistically significant. Maybe that drug isn't doing anything at all. It's not helpful at all. It's just a chance occurrence, all right, that the group that got the drug happened to run just a little bit better on average. All right, so in order for me to know that my drug actually worked, the difference between those who received the drug and those that didn't needs to be big enough that we can be relatively confident that that drug did have that beneficial impact. So, for example, if the group that got the performance enhancing drug, if their mile time is 30 seconds better on average than the control group, clearly the drug is having a positive impact. But if it's 1 second, it might be having no impact whatsoever. But where do we draw the line? How much faster do they have to be? Do they have to be 10 seconds faster? Do they have to be 15 seconds faster on average in order for us to conclude that the drug is beneficial? In order for us to know, we have to use the sampling distributions. All right, so we're going to kind of just use sampling distributions a little bit, and as we get used to using them more and more, I'll give fuller and fuller descriptions of what the sampling distribution is. But it's going to be needed. For example, on these COVID vaccine trials, they had to use a sampling distributions in order to conclude that the vaccine was actually effective. Okay, so let's go ahead and work with a sampling distribution. So for your assignment, I'm going to have you guys go to this page. When you go to this page, just press begin right up here. So let's start off with what we have right here. This is what's called a population. So there's all sorts of different populations. We'll say that this is the population of U.S. men, and in particular, it plots how many days a month U.S. men work out. How many days per month the U.S. men work out. Now, some U.S. men work out every single day. That would be these people over here. Some U.S. men never work out. That would be these few people over here. And we can see the mean or the average for this is 16. So we'll say the average U.S. Man works out 16 days per month. All right, and we'll say that this is the population data for U.S. women. So U.S. women on average work out, we'll just say 11.5 days a month. All right, I'm completely making these up just so that there's a contrast. All right, don't read anything into these. All right, but we've got these two different parent populations. Now, only, all right, I'm going to invoke the gods here. Only the gods know how many days on average all U.S. men work out. What's the average of all U.S. men? Only the gods, only omniscient beings would know what that actual average is. A scientist would never go and look at every single man in the entire U.S. country. They would look at a sample of this population, not every single one of them. So I'm going to look at a very small sample. All right, it's going to be a sample of just 5 people. All right, so here are our 5 people. All right, so we had 2 men who worked out about 16 days a month, 1 man that worked out 17 days a month, another man that worked out like 21 days a month, and the 5th man works out 23 days a month. And here's their average. All right, of these, in my sample of 5, the average days per month that are worked out was, it looks like 18. All right, so this blue block represents the average. Now I could look at another sample of 5 people. All right, and look, this sample came from the exact same population, but it has a very different average. All right, the first sample had an average of 18. The second sample, it looks like it has an average of 15. All right, and I could draw another sample of 5 men from this population. And boom, there's another average right there. And it's largely this, so the data look different for this third sample, but they have pretty much the same average as that second sample that I just took. All right, so now what is the sampling distribution? The sampling distribution is if I look at every sample of 5 people that I could possibly take from this entire population. And I'm going to build more on that. I'm going to have you guys work on that in the next class. But I'll go ahead and repeat that now because repetition is good. The sampling distribution in this case would be a plotting of the averages of every single possible sample of 5 men that I could take from this entire population of U.S. men. All right, and so what that sampling distribution is going to look like, if it's going to plot the average of every single possible sample of 5 men, is it's going to look something like this. I'm going to press this button, and it's going to draw 100,000 samples, each having 5 people in it. It's going to draw 100,000 samples from this population and plot their averages right here. So I'm going to go ahead and press that. All right, and so that's what the sampling distribution, the distribution of sample averages, looks like that. Now, if I were to do the same thing for the female data, all right, so here's the female population, the American women population. If I were to take 100,000 samples, each having a sample size of 5, all right, I would get a sampling distribution that looks like this. All right, so a little bit different from the one that we just took. All right, so I'm going to go ahead and stop there. I have an assignment that will prod you guys to think more about sampling distribution, but we're going to go ahead and just stop the lecture right here.